Hi everyone, today we're doing notes for 7.2, estimating mu when sigma is unknown. So we're looking at the t variable today. X has a normal distribution with mean mu for samples of size n with sample mean x bar and sample standard deviation s. The t variable t equals x bar minus mu divided by s divided by square root of n. So if you notice, this is the same as the z-score. Your value minus the mean divided by the standard deviation. And so here we're going to have, it says with degrees of freedom n minus 1. If the degrees of freedom are not in the table, we're going to use the closest degrees of freedom in the table that's smaller. Otherwise, we can use the calculator to figure this out. Properties of a t-distribution. The distribution is symmetric about the mean 0. The distribution depends on the degrees of freedom, which is n minus 1. The distribution is bell-shaped but has thicker tails than the standard normal distribution. As the degrees of freedom increase, the t-distribution approaches the standard normal distribution, and the area under the entire curve is 1. So we need to find the critical t-value for a 90% confidence level for a t-distribution with a sample size n equals 9. So our correct degrees of freedom, remember we do n minus 1, so in this case we would have 8. Now we can find this, there is a table 6, which is on page A24 in the book to find these values. So it says find the value for t of 90 for a sample of size 9. So again, our degrees of freedom are 8 that we're working with. So if I have my distribution, I know if the middle 90% is shaded, then that means we have 5% on each tail. So we're going to use the 5%, right, to get this t value. So we're going to look at 0.051 tail, and we're looking at the left. And so we get our t is going to be 1.860. For the next one, find the value of 95%, or t of 0.95. Again, same sample size, is 9, so our degrees of freedom are 8. So now if this is our curve, we want the middle to represent 95%, leaving 2.5% on either tail. So again, we're going to use this part here to find our t. So we're looking at 0.0251 tail, again on the left, and our t of 0.95 is going to be 2.306. Now we can also do this in the calculator. So when we're looking at our calculator, we're going to go to our same menu, that distribution menu. Remember, you hit our second, and then, whoops, variables. And so when we're doing this, if, for example, we're doing the 90% confidence one, okay, then you can do this as inverse t of 0.05, comma, 25. Okay, if this was the same case here. We're putting in our degrees of freedom. For 90% confidence, I also want to point out you can do either the 95% or the 5%. Okay, either way, you're going to get, in this case, you get negative 1.708. This case, you get the positive 1.708. So you see it's the same value because the curve is symmetric. Okay. Margin of error. So our margin of error formula is TC, which we just learned how to calculate, times S divided by the square root of N. And then our full confidence interval formula is we're going to be doing x bar plus or minus TC times S divided by the square root of N. So again, you see this is the same thing. It's your point estimate plus or minus the margin of error. Okay, suppose an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horse. Reconstructions of the skeletons of these 7 miniature horses show the shoulder heights in centimeters to be, and then we have our list here. So I want you to do A and B and find the mean and sample standard deviation. Okay. So if you recall, remember you can enter your data into L1. We do stat, calc, and then the one variable statistics. And so our mean comes out to be 46.14, and our standard deviation is 1.19. Notice I'm using S bar and S sub x because these are coming from the sample data. Okay, so in this case, we have our n equals 7, which means our degrees of freedom equals 6. And now we have enough information to do C here. I'm actually going to change this 95% confidence interval. Let's change this to 99. That way we're doing examples with different types. All right, so let mu be the mean shoulder height in centimeters for this entire species of miniature horse, and assume that the population of shoulder heights is approximately normal. Find a 99% confidence interval for mu, the mean shoulder height of the entire population of such horses. So our formula, x bar plus or minus TC times S divided by square root of N. Well, we need to find our T of 0.99. So we can use this doing the calculator or the chart. And so if we're doing 0.99, that's 99% is in the middle. So you have 1% split between the two tails, which means you really have 0.5% on the left. So you're looking at 0.005 on the one tail to the left. Okay? So this comes out to be 3.707. So we have 46.14 plus or minus 3.707 times 1.19 divided by square root of 7. So this gives us 46.14 plus or minus 1.67. And so then we end up with 44.47 to 47.81. Now you can also do this in the calculator. We're going to use what's called the T interval. Okay, and we're going to use the data that we entered in the calculator. Okay, so you're going to go to stat, then arrow over to tests. We're going to choose number 8, which is the T interval. Oops. And then by list, it should say L1. Frequency should say 1. And then our confidence level will be 0.99. And then you go ahead and hit calculate, and it will calculate the confidence interval for you. Okay. Here's our next one. A company has a new process for manufacturing large artificial sapphires. In a trial run, 37 sapphires are produced. The distribution of weights is mound shape and symmetric. The mean weight for these 37 gems is x bar equals 6.75 carats, and the sample standard deviation is S equals 0.33 carats. Let mu be the mean weight for the distribution of all sapphires produced by the new process. So check requirements. Is it appropriate to use a T distribution to compute a confidence interval for mu? So it says here that we are mound shape and symmetric. And we also have that our sample size is 37 sapphires. So yes, this is appropriate. We know that it's mound shaped and symmetric. and our n is equal to 37, which is greater than or equal to 30. All right, what is our degrees of freedom? So degrees of freedom, remember, is n minus 1. So 37 minus 1 is 36. All right. For C, it says use table 6 or your calculator to find t of 0.95. Note your degrees of freedom is not in the table. Use the degrees of freedom closest. That is smaller. So I want you to find this one, please. Okay, if you did this using the table, we're doing 0.025 in the tail. And so our degrees of freedom is about 35. And so this is 2.030. If you chose the calculator, you're doing 0.025 or 0.975. Again, you're just adding that 0.25 to it. And so then from here, we have our degrees of freedom is 36, and the calculator we get 2.028. Okay. So next we have to find the margin of error. So margin of error formula is TC times S divided by square root of N. So I'll do this with the table value. So we have 2.030 times 0.33 divided by square root of 37. And this comes out to give us 0.11. For E, we have to find a 95% confidence interval for mu. So remember, this formula is x bar plus or minus ME, our margin of error. So I want you to find this now. Okay, so we have 6.75 plus or minus 0.11. So this comes out to give us 6.64 to 6.86. We can also do this in the calculator. So if we do t interval in the calculator, we'll come out with 6.64 to 6.86 as well. Okay, to do this one, again, we do stat, tests, we're doing 8, the t interval. But in this case, we have to choose stats because we did not enter data. And so your x bar is 6.75, your s sub x is 0.33, your n equals 37, and then your confidence level is 0.95, and then you hit calculate. All right, so to interpret this, what does the confidence interval tell us in the context of the problem? So the company can be 95% confident that the interval from 6.64 to 6.86 carats captures the population mean weight of sapphires, produced by the new process. All right, and so last here, it just says, what distribution should you use for X bar? So you have to look at the problem statement. And so first, last section, we did when our sigma is known. When sigma is known, we're going to use the normal distribution with the margin of error. So our margin of error here, we use the ZC, and then we're using sigma divided by square root of n, and this is our Z interval. When our sigma is unknown, that's what we did today, we're going to use the t distribution with the similar margin of error, but we just use our TC as our critical value with our degrees of freedom n-1, and this is when we use the t interval. And that's where we're stopping for today.